Good evening, Ravi Kumar sir.
You are able to hear me? Good evening. Good evening.
Yes, sir. Sir, actually participants are joining, sir.
Okay, no problem. I'll wait. No issue.
Within 5 to 7 minutes, we'll start, sir.
No problem. Yeah.
Thank you, sir. Sir, meanwhile, I'll introduce Dr. L. Jayahari, sir. Jayahari, sir, are you there, sir?
Yes, ma'am. I'm there, ma'am. Hello.
Sir.
Yeah, good evening.
Good evening, sir. This is Dr. Jayahari,
Yes.
Dean R&D from KG Reddy.
Yeah, good evening. Hope everything is going on well till now.
Yes, sir. 2 days is done.
Yeah.
Now this is the third day. So hope we'll enjoy the 2 days session, both the session and.
Yeah, hopefully. Yeah. Thank you.
Thank you, sir.
Sir, Jayar, sir. Hello.
Yes, sir. Who is this?
I am Praveen, sir.
Yeah. Wait a minute, sir. Wait a minute.
Okay, sir. Is it
Can
audible,
you
sir?
accept-
My voice is.
Yeah, your voice
Is
is
my
clear.
voice is clear? Okay.
Yeah. Samithikam,
Okay.
shall we start?
Yes, sir.
Praveen, sir.
We can start, sir. Praveen, sir, we can start. Praveen, sir.
Sir, shall I wait or shall I start?
Praveen,
Yes,
sir,
sir.
please. Please
Yeah.
start.
Yeah.
Welcome, Praveen, sir, today's
Yeah.
moderator. So please
Yeah.
introduce guest speaker, sir.
Yeah. Okay. Thank you, very. Good evening to all. So I, K. Praveen Kumar, Department of Mechanical Engineering, KG Reddy College of Engineering. Now I welcome to all participants and speakers. Firstly, I thankful to Dr. Jayhari Garu, Professor, Dean R&D, and K. Kalpana Garu, Head of the Department Mechanical Engineering, and Samyukta Garu, head CIST, for giving an opportunity to participate in this program, and also to introduce Dr. Ravi Kumar sir, speaker of this session 1. Now, I am very happy to introduce Dr. Ravi Kumar Team Singhu. Now, the sir is currently working as professor in the Department of Electrical Engineering, IIT Hyderabad. He has been with IIT Hyderabad since July 2013. He worked in the Department of Electrical Engineering, IIT Hyderabad, as an assistant professor from July 2013 to November 2017, and also as an associate professor from December 2017 to October 2023. Prior to joining in IIT Hyderabad, Dr. Ravi Kumar worked as a senior executive technology at Global R&D Center, Crompton Greaves Limited, Mumbai from June 2010. Dr. Ravi Kumar did his BTech from RVR and JC College of Engineering in 2002 under Nagarjuna University. He obtained his MSc Engineering and PhD degree both from Department of Electrical Engineering, IISc Bangalore in 2004 and 2009 respectively. He also served as a senior research associate at the Department of Electrical Engineering, IISc Bangalore during the December 2009 to June 2010. His research interests are in the fields of integration of renewable energy sources, AI technologies applications for power systems, power system protection and power electronics applications to power systems. He authored 23 journal publications, 65 conference publications, and 2 book chapters. So this is a brief introduction about Dr. Ravi Kumar Bhim Singh sir. Sir, I request please take over the session, sir.
Yeah, thank you, Dr. Praveen, and thanks to the organizers.
Thank you, sir.
I will share my screen. I think it is not allowing me to share the screen.
Chari? Chidambara Chari?
Already done sir course.
Okay. And in between, we are having some disturbances. If any participant is unmute, then mute immediately. Ravi Kumar sir already he has given host to you. So please.
Yeah, I think it is not allowing me to share it. Open settings. I think. 1 minute. Yeah.
Okay.
You are able to see my screen now?
Yes, sir. Yes, sir. We
Yes,
are
sir.
able
The
to see.
screen is visible.
So anyhow, good evening to all. Okay, so the current FDP trust area is very nice. Okay, so energy, sustainability, and climate change, emerging topic in this current scenario. Even the title of the FDP is Harnessing Sustainable Energy for Climate Resilience, a faculty development perspective. So the present, so the title of my presentation is Renewable Energy Integration and the challenges and how to improve the integration of the renewable energy sources. That is the main topic for today's discussion. Okay, so in this presentation, I will be discussing about when we have to integrate the renewable energy sources, what are all the challenges that we'll be facing, and to avoid come across, okay, to reduce these challenges, okay, so to overcome the challenges, okay, what are all the improvements that we have to do it. So that will be discussed in this today's presentation. Okay, so the contents of this presentation are as follows. Okay, initially we'll have some introduction, and we'll have some introduction for the challenges and what are all the control schemes that are there, and how we can improve the resiliency in grid connected renewable energy sources, and to improve it, what are all the proposed control schemes are there, and the comparison of the proposed method with the already existing control techniques. Okay, that will be discussed in this presentation, and finally we'll have conclusions. Okay, so I just want to know, okay, so all the people are from the mechanical engineering background?
Sir,
So
actually combination of all, sir.
all the parties.
Mechanical, yes, sir. Mechanical, electrical, civil, and CSE also there.
Okay, yeah,
Mm.
fine, yeah. Okay, so then I will try to present it in a way like it will be beneficial for all the participants. Okay, so little bit I will try to make as much as possible to be understandable for all the people. Okay, so initially we'll have some introduction why, like what are all the challenges that we'll face when we are integrating the renewable energy sources to the grid. So on that one we'll have some slides. Okay, then how we can overcome this one, what are all the challenges that generally we'll face it, and how to address those things. Okay, those things we'll see. That is the overall content of this presentation. So this is the typical power system. Okay, this is the general structure of the power system. So where you can see, so this part is the generating stations. Generally, the generating stations are like thermal power generators, gas-based power generators, hydro-based power generators. Okay, so like that. Okay, so the generating stations will be there, and the power that will be generated from the generating stations are at low voltages. Low voltages in the sense, okay, we should not say low voltage like 400 volts, 500 volts. Okay, so low voltages means around 10 kV, 10,000 volts, 11,000 volts, up to 22,000 volts. So that is the typical power generation at the generating stations. So then at low voltages, we cannot transmit the power to the consumers. Okay, so because the generators will be there at some locations. If you see our India, so the power generations will be there at only at various locations. Okay, so like you have NTPC, National Thermal Power Plant. So we have hydrothermal power plants which are like in the eastern side, but more load centers are in the Delhi, Mumbai. Okay, so Hyderabad, Kolkata. These are the things. Okay, so now the power has to be transmitted to the customers. That much bulk amount of power cannot be transmitted at the low voltages. Okay, it has to be step up to the higher voltages and then has to be transmitted. So the transmission line voltages will be 765 kV, 500 kV, 345 kV. It is general, but in our India, we will be having like 132 kV, 220 kV, 400 kV, 765 kV. So this is the typical transmission line voltages in India. So then again, when it comes to the customer side, okay, so the voltage has to be stepped down to 33 kV, 66 kV, 11 kV, and 430 kV, 430 volts, and 430 volts or 230 volts. So this is the typical voltage. Okay, so now the power is transmitting from the generating stations which are far away to the load centers through these transmission network. Okay, we will have in between the transform, step-up transformers, step-down transformers. All those transformers will be there in between. So now the transmission network. Okay, so the expansion of this transmission network is not as manifold as the way the generation or load is being changed. Okay, because they occupy long distances. Okay, so that's why these transmission network always operate in a quasi steady state operation, means they operate very close to their design limits. Okay, so now the same these electrical network, if you are representing like this one, where you have the generation stations and you have an utility grid. At utility grid, from the utility grid, there will be a distribution network. At the distribution network, we will be having these distribution loads. Okay, so it can be a household appliances, apartments, or some type of industrial loads. Okay, so those things will be there, and they also have their own backup supply. Okay, so in terms of diesel generators. Okay, so now as we have seen, the generation is increasing to meet the load, but in between the expansion of the transmission is not as far as with the generation and distribution. So most of the times these utility grid will be facing some issues. Okay, so what type of issues it is facing is like, so it is facing the quasi steady state operation. Okay, most of the times the transmission network is operating very close to its design limits. Design limits means if the transmission line capacity is 100 megawatt, okay, it is operating very close to 95 megawatt, 90 megawatt, and that's what we will say. The available reserve is very less. Okay, so if the line gets overloaded, it will trip. Again, it will create overload tripping. It will load other lines. Okay, so this is one issue. Like again, increasing the energy needs. Okay, so the power requirements by the loads are being increasing. Again, to cater that one, the transmission network has to be planned. Peak load shortage. Okay, so again, to meet the peak load, okay, generally the peak load will be available only for a specific amount of time. Okay, so only to meet that one. Okay, so we cannot establish a new generating plant. Okay, so these are some of the issues like fossil fuel depletions. Okay, so the coal based, gas based, these things. Okay, the depletion is there in these resources, and power quality and reliability issues are there, and rural electrification is one thing where, okay, so most of the rural places, the availability of the power is limited. Even if it is available, the continuity of the power is also less. Okay, so these are all some of the issues generally faced by the power systems. Okay, then how to meet these growing demand for this electricity? Okay, so this is one has to address it. Okay. So one way to address this is, okay, so connect some type of renewable energy sources. Okay, so small PV sources. And the concept is like local power generation to the local power generation being connected, which generally we'll call it as a renewable energy sources or distributed energy sources. If you connect them, okay, so at least this can be solved. But again, in this picture, we are connecting at the utility grid. Okay, so again, the problem will not be solved. Okay, so now another way to connect is like, so at the distribution network. Okay, so the renewable energy sources will be connected to the distribution network. So now this local generation is generally made to meet the local power requirement. So it works on the concept of local power generation for the local loads. Okay, so this is the philosophy which has been initially introduced. Now again, we are coming back to the same concept to introduce these renewable energy sources. Okay. So this is one scenario. Okay, so this is South Indian scenario. Okay, so typically, okay, so this data we have taken from one of the place in Hyderabad. Okay, so in one on the top of a IT building. Okay, so this the typical scenario will hold good. Okay, all over the South India. Okay, so now the the graph, if you see, so the top one is the solar radiation graph, okay, over a period of 12 months, and the bottom one is the profile of wind velocity. So these are average values. Okay, so in January, February, how this wind velocity is there, and the solar irradiation. Okay, the solar irradiation is proportional to the power that is being generated from by the PV. Okay, so now if you see these things, okay, this is the southern part of the Indian faces a mix of tropical dry and wet climate. So in this place, okay, so we have an average solar radiation of 5.34 kilowatt hour per meter square with a maximum radiation of more than 6 kilowatt hour per meter square. So similarly, we have a wind profile, okay, so an average wind velocity of 4.14 meter per second. So from this data, it can be observed that, okay, so here you can see like, okay, if you observe these things, the orange color bar charts. Okay, so whenever the solar radiation is reducing, during that time you can see a wind velocity is more, the profile of wind velocity is more. Okay, so wherever the solar radiation is more, during that time we have less wind velocity. Okay, so from this one we can see like, okay, if you use these two things together, okay, so this can make the total energy availability almost constant throughout the year. Okay, so this is what the observation we can make it from these two graphs. So apart from these ecological opportunities we have in India, so government is also having certain initiatives. Okay, so generally the initiative started way back. Okay, so initially the Electrical Act 2003. Okay, so this has given a trust to the distributed generation in the context of rural electrification. Means, okay, so the rural energy needs are to be catered by a combination of conventional as well as the renewable energy based microgrids. And National Electricity Policy 2005, this is an extension to the previous Electricity Act. Okay, so means, so wherever the rural electrification systems are not reliable, okay, so we have to make them reliable by using the standalone or decentralized distributed generation facilities. Okay, so this is where the utility grid is not feasible or not in a position to extend it. So another one is a diesel abatement scheme. Okay, so in the previous slides we have seen, like, okay, so there are some diesel generators, they pollute the environment. Okay, so to reduce the diesel content usage, okay, let us use the renewable energy content. Okay, so for that one, Government of India is also giving some subsidies. Okay, so it is giving almost like 40% of the total installation cost for non-profit making organizations, and it is reduced to 30% for profit making organizations. Anyhow, okay, it tries to promote the augmentation of the renewable energy source based installations to reduce the pollutions from the gas based or diesel based generating stations. And solar energy scheme. Okay, so here this scheme tries to promote the PV generation plants. Okay, so here also the government is giving some subsidy. Okay, so government general category states for all beneficiaries like 30% subsidy on total capital cost or 5% interest loan on 80% of the benchmark cost. Okay, special category states for domestic and non-commercial beneficiaries. So it is almost like 60% of the capital subsidy, 30% of the capital subsidy for those who are availing accelerated depreciation, or 5% of the interest loan on 80% of the benchmark cost. Okay, so this is one scheme to promote the PV installations. Other schemes like Rajiv Gandhi Gramin Vijdikarna Yojana, remote village electrification. So this also provides around 90% of the capital cost, subsidy on the capital cost for the rural electrification projects that develop decentralized distribution generation plants. So now if you see our Indian scenario, especially for the southern states, okay, so we have the mix of the climatical changes and the ecological opportunities also promoting. Okay, so it is supportive, and apart from that one, the government initiatives are also there to encourage the renewable energy content to the power generation. Okay, so even the Ministry of National Renewable Energy Ministry is also mandating to establish a minimum renewable energy content in the commercial establishments like universities, industries, okay, residential complexes, government buildings. Okay, so to promote the microgrid development in India. Okay, so this is in this picture we can see the all over India total power installed capacity value. So this is as of October 2024. Okay, so we have almost like 454 gigawatt of power generation capability has been installed. So out of which the coal is around 211 gigawatts, and the renewable energy source content. Okay, so it includes the hydro, nuclear, gas, lignite, coal. Okay, so the so it includes renewable energy sources like solar, wind, small hydro, all those things. Okay, so these are around 156. Okay, so if you see here, okay, the renewable energy content is almost like 35%. Okay, as on October 2024. And the renewable energy content over a period of time, if you see from 2000 to 2024, okay, so the content has grown up. Okay, so you can see like initially it was like few megawatts. Okay, so less than 10,000 megawatt, but now it is almost like reaching to 160, 170 gigawatt. Okay. So then what is the problem? Okay, so anyhow, we are having these renewable energy content being installations are going on increasing, but what is the problem? Okay, so the problems are like from the technical side. So the technical challenges in the performance aspects of the microgrid, if you see, there are challenges in terms of the power quality and reliability, challenges in terms of the frequency and voltage stability, challenges in grid synchronization monitoring, challenges in system protection due to bidirectional power flow, challenges in power balance due to renewable energy source uncertainty, challenges in economic dispatch, challenges in system control. Okay, so these are some of the technical challenges. Okay, so if you see these things in detail, okay, the challenges in power quality and reliability is defined as the deviations in the current and voltages and frequency. Okay, so generally we will see these current and voltage frequency deviations, but these are all not desired. Okay, they are all undesired, that leads to failure of the loads. Okay, so the microgrid also contains some unbalanced loads, nonlinear loads, which causes severe power quality issues. Okay, so if you see sinusoidal waveform, if it is a pure sinusoidal, that is well and good, because most of the equipment they are developed based on assuming that okay, the voltages or currents are sinusoidal in nature, but because of the loads, nonlinear loads that are presented, okay, that will cause power quality issues. Okay. Moreover, the power electronics based, most of the times when it comes to the microgrid, the renewable energy sources, they are connected through an inverter. Okay, so we generally call this one as a power electronics based voltage source inverter that is used in microgrid. So it itself acts as a source of harmonic generation. Okay, so therefore, so it is important to ensure suitable power electronics based voltage source topology. Okay, so to reduce the harmonic content from itself, from itself. Okay, so both in the operation of micro operating in islanded mode and grid connected mode. Islanded mode means so it is not connected to grid, it alone supplying to the loads. When it is grid connected, okay, it has to follow the grid, because whenever it is connected to grid, so both grid, it has to follow the grid to support the grid. Okay, so reliability is another major performance aspect in the microgrid's operation. So this can be of two types. One is system reliability and another one is a network reliability. When it comes to the system reliability, is majorly affected by the power management issues occurs due to the changes in the renewable energy sources. So if you see the voltage, if you see the PV, okay, so whenever you have a solar radiation, then the output will be there. When the solar radiation is reducing, the output from the renewable energy source also reduces, okay, which is not in our control. Even wind plant, okay, so whenever you have a voltage, whenever you have a wind velocity, sufficient wind velocity, the output from the wind power plant will get it. Okay, so otherwise you will not get. Okay, so these are not in our hand. Okay, we cannot control the power output from these renewable energy sources. Okay, so whenever there is a input solar irradiation or input wind is available, then only we'll get it. Otherwise, the output from these one will drastically reduce, which in turn will create the differences in the output that is being generated. Okay, so then you will have a load and generation mismatch, which leads to the frequency changes. Okay, so any frequency or voltage oscillations in the utility grid side has a direct effect on the power oscillations and load voltages on the microgrid. So these undesirable sudden changes in the system frequency and voltages may create issues with the safety of the various sensitive microgrid loads. Okay, apart from this one, okay, we have a network reliability. So it is majorly affected by the communication between the control equipment and the measuring devices. So some challenges are in like from the yeah. in the frequency and voltage stability. Okay, so if you see a general power system, okay, so nowadays this renewable energy content is coming into picture. Previously, everything is synchronous machine based generating stations. Okay, so the power system stability indicates. Hello. Yeah. So it indicates the ability of an electrical power system to regain a state of operating equilibrium after being subjected to a disturbance. Okay, so that generally we'll call it as stability. Okay, so generally we will have this frequency based instability, voltage instabilities will be there. Okay, so when it comes to the frequency stability, in general bulk power systems where it is being driven by synchronous generators, so they have a huge inertia. Okay, so because of this one, whenever there is a disturbance occurs, the kinetic energy stored in these huge masses will compensate the oscillations. But in case of microgrids, they have negligible inertia because of the power trans based voltage source inverters are being connected. Okay, so because of this low inertia, this leads to undesired frequency deviations in the islanded operation. Okay, so and again it becomes like uh, um, very difficult when it is being connected to a weak grid. Okay, so in a multi-microgrid environment, local oscillations may emerge from the interaction of these control systems of different microgrids, so which requires thorough small signal stability analysis. And moreover, the transient stability analysis are required to ensure smooth operation between grid-connected mode of operation to the islanded mode of operation. So when it comes to the voltage stability, okay, so voltage stability can be defined as the system ability to maintain the nominal voltages at all the buses in its under normal operating conditions and are being subjected to a disturbance. Okay, so load unbalances, voltage sag or swell, reactive power imbalances, etc. So these are the prime factors leading to the voltage stability issues in microgrid. So the regulation of the AC voltage of the microgrid is a matter of maintaining an equilibrium between the source and the load reactive power. So the reactive power varies with respect to the type of load being connected to the microgrid as compared to the active power and reactive power, active power and active load variation, where the energy stored in the rotating masses can compensate. But whereas in case of reactive power, the reactive source and load storage is not possible. Okay, so in such a case, synchronous generator based conventional power plants, the flow of reactive power can be controlled by the excitation control. But in case of a microgrid based controls, okay, so this will be a little bit challenging. Okay, so this is another challenge generally will be faced in when it comes to, when the renewable energy source based microgrids connected to the grid. Okay, again, challenges in the grid synchronization monitoring. Synchronization to the utility grid is an essential requirement to the renewable energy source based microgrid to enable the grid export or import facilities to ensure continuous and stable supply to the loads. So as per the necessary conditions of the synchronization, so whenever you want to have a proper synchronization, the magnitude should match, the phase sequence should match, phase angle should match, and frequencies are to be matched. Okay, so that's why these phase angle, magnitudes, frequencies, sequence, these things has to be continuously monitored. Okay, so what will happen under certain disturbance conditions? The calculation of these things will be inaccurate. Okay, so if you have inaccurate things, the proper synchronization is not possible. So that's why accurate and fast phase angle detection methods are required for the reliable power delivery as well as to control undesired trippings at the PCC. PCC means point of common coupling. So generally under unbalanced conditions, okay, the negative sequence component of the microgrid voltages affects the phase angle detection. This is a part of a method. Okay, so this leads to the undesired oscillations in the frequency as well as it affects the overall control systems. Okay, so due to these apart from these things, okay, the standard operations that are being imposed by the utility grids, okay, so they have to follow the grid codes. So if they are not following the grid codes, okay, so then they'll impair they will penalize the people. Okay, so the grid monitoring plays an important role in deciding when the microgrid system should be terminated from the utility grid. So hence the detection algorithm should be capable of tracking accurate voltage magnitude, phase angle, line impedances, and frequency at being robust to the disturbances to address all these aforesaid challenges. And challenges in the system protection due to bidirectional power flow. Previously, if you see the general structure of the power systems, the generation, transmission, and distribution, everything is okay. So from the distribution also, from the distribution side, the loads, it is a unidirectional. Okay, so but when these renewable energy sources connected, the distribution is also becoming like a active distribution. So the interaction of these renewable energy sources to the loads and the utility grid through these power electronics based voltage source inverters has raised concerns about safe operation and protection of the connected loads. So while these distribution feeders were initially designed for unidirectional power flow, integration of these renewable energy sources units at low voltage levels can cause reverse power flows and lead to complications in undesired power flow patterns, protection coordination, fault current distribution, and voltage and frequency control. So with this bidirectional control on the power flow, it is possible not only to specify the exact amount of power supplied by the utility grid, but also the feedback power from the microgrid to the utility grid during lesser power demand in the microgrid. So, so for better performance, efficient power management, precise signaling to the power equipment is very much important to achieve the control over the power flow between the utility grid and the microgrid. And also protection of these loads that are connected to the both microgrid as well as the utility grid during the fault is always a major concern. So also because of these uncertainties in the renewable energy sources, maintaining the power balance is also a challenging task. And system control. Okay, so because if you see the controllers are major contributors in achieving the desired performance. Okay, so the controllers plays an important role in transmitting the required amount of P and Q. Okay, so the challenges in the system control also plays an important role. Okay, so the controllers are supposed to provide manifold tasks against different operational challenges as described, like transition between islanded and grid connected modes, demand side management and control, specific control requirements with respect to the different architectures like DC bus architecture or AC bus architecture or hybrid architecture. So output voltage and current control and active power and reactive power control. Okay, so these are all some of the challenges that has been posed by the power electronics based voltage source inverters. Okay, so challenges in the economic dispatch. So economics of the microgrid is mainly depending on the regulatory and economic framework of renewable energy sources in the respective regions or countries. An appropriate dispatch of the renewable energy units participating in the operation of microgrid can significantly reduce the operating costs, thereby increase the profits. So reliability considerations must also be taken into account in the dispatch of the units, especially in the standalone operations. So if you see these technical challenges in the performance aspects of microgrid, for the fruitful performance, okay, so the microgrid majorly relies on the following factors. Okay, so one is intermittent nature of the energy sources, because the renewable energy sources, PV or wind, their power output depends on the solar irradiation and speed. So they are intermittent in nature. Design of suitable power conversion devices, design of effective controls for controlling the power converter operation, and suitable architectures to interconnect all these constituents. Okay, so now ineffective addressing of any of these factors can degrade the microgrid's key performance aspects such as power quality, reliability, stability, protection, etc., especially during disturbances. Okay, so how to address the issues faced when the renewable energy source is connected to grid. Okay, so majorly the power quality concerns raised by the intermittent nature of the renewable energy sources. So somehow this can be addressed. Okay, when you have a storage, okay, and switching device based power electronics based inverters. Okay, so anyhow they themselves inject harmonic content into thing. Okay, so by using multi-level inverters, okay, so even we can reduce the total harmonic content to the grid. And when it comes to the wind or solar farms, they provide lesser grid support during disturbances. Under normal conditions is fine, but under under disturbances or emergency situations, they don't provide any support to the grid, or they provide very less support to the grid. Okay, so for faithful renewable energy based microgrid installations, it is recommended to adhere to the some of the guidelines given in the standards like IEEE 141 or IEEE 1547, IEEE 519 or Central Electricity Authority. They impose some guidelines on the renewable energy content connection to the grid. Okay, so any renewable energy source in connection to the grid, they have to follow these grid codes. So what are all the standard limits? Okay, if you see the standard limits for the performance evaluation, there are some performance indices are there. Okay, so like wave shape, how it should be there, stability restoration time, how it should be there, deviations, how it should be there. Okay, so what are all the standard limits? Okay, so these are all some of the standard limits as per the standards. Okay, so like here you see voltage wave shape. Okay, means the distortions, how much distorted. Okay, so there should not be any deviations. Okay, and rate of change of voltage. Okay, so they should be limited to plus or minus 3 volts per second. So voltage deviations plus or minus 10%. Positive sequence voltage, negative sequence voltage. So positive sequence voltage should be very close to 1. Negative sequence voltage should not be there. Voltage imbalance should be limited to 3%. Over frequency and under frequency plus or minus 2%. Rate of change of frequency plus or minus 1 Hz per second. And over voltage and voltage sag 10% and 40%. And if there is a voltage spike, it should be limited to 33%. Okay, so and stability restoration time, it should be as fast as possible. So this is what the standard limits that are being imposed as per the standards displayed here. Okay, so now, so renewable energy source integration, if you see here, we have PV. Generally, you have the inputs. Okay, renewable energy sources we will call the PV, fuel cells, and wind. Okay, so here we have given battery. Actually, battery is not renewable energy source, but so for the proper operation of these things, generally battery will be connected. So now the inputs are like renewable energy sources plus battery. Okay, so they form the input of the input, like they are power supply sources. Okay, if you categorize these things, okay, AC sources and DC sources. AC sources are wind plants and DC sources are, okay, PV fuel cells. They generate power in DC. Okay, so DC power generating sources, battery. And if you see the requirement from the load side, okay, majorly they are like R load, RL load, RLC type of load. Okay, so when you're connecting the sources to the load, it becomes like islanded operation. But the moment when you're, okay, so you are exporting to grid, this becomes like a grid connected. Okay, so now these energy sources are the power sources. Okay, so the output is connected to load, and excess power, if it is there, it will be connected to the utility grid. Okay, now to connect these things, okay, so there are various architectures, because if you consider this wind plant, also will have some type of power trans based conversion. Okay, so essentially, if you consider this wind plant is also like it is connected to its local DC bus. Okay, so all those things will be connected to a DC source, DC bus, and the output is, okay, either it is connected to the utility grid or load. So they are all AC in nature. Okay, now we have to connect these AC DC power sources to the AC network. So we require a converter in between. Okay, so we require a DC to AC power conversion system is required. Okay, so how we can do this conversion? Okay, so here majority of the sources are DC in nature and the requirement is AC. We need a DC to AC power conversion. So how we have to do this power conversion? Okay, so initially people they used to use the DC motor coupled synchronous generator for converting the DC power to the AC. Okay, so this is a rotary, because these are all real machines, DC motor coupled to synchronous machine. So the DC sources are being connected to the DC motor input, and from the synchronous generator output, it is connected to the building loads and the utility grid. So that's why this is a rotary inverter we'll call. Okay, so inverter means it is a DC to AC conversion, but we are using the real rotary based conversion, real machines. So that's why it is a rotary inverter. So the problem with this type of conversion is it is limitations in efficiency, because you are using a real machines, rotating machines, their conversion efficiency is limited, and space requirements for a small conversion like 10 kilowatt, 20 kilowatt, it is fine. But if it has to convert few megawatts, okay, so the requirement of the DC machine and synchronous generation sizes will increase. Okay, so whenever you have a space limitations, and that too high load centers, okay, so this is very difficult. Deployment cost for low to medium range load centers is higher. Okay, another conversion is the static converter, where the power electronics based converters, when they comes into picture, the renewable energy conversion from DC to AC becomes easier. Okay, so the advantages are like use of power electronics devices in the microgrids design gave birth to the several modular and efficient installations all over the worldwide. Okay, but these things, because you are using a power electronics based converter, it leads to severe power quality concerns, like they themselves generate the harmonics, and there are some inertia issues in this part. So this is the typical connection diagram when it comes to the real electrical machines based conversion. So this is the DC motor and synchronous generator. So each one will have their own DC motor control and synchronous generator control. So this is the power electronics based static converter. This is a three-phase inverter. So three-phase inverter is being controlled by a power electronics based multi-level inverter controller will be there. Okay, so the typical control systems looks like this. Okay, you have a droop controller and a voltage controller and current controller. So this one will be used to generate the PWM signals, which in turn will control the switchings of the MOSFET or IGBTs, which in turn will control the P and Q that are being emanated to the grid. Okay, so here if you see, this is the droop controller. So you will have this the VD naught, VQ naught, ID naught, IQ naught. Okay, so this will be measured, and you have a PQ calculation power, real P, real Q, sorry, active power, reactive power calculations. So then this will be compared with the reference values. Okay, so by using these KBKI, okay, so the droop gains functions. Okay, so it will generate VD reference and omega. While comparing this one, you will get theta. By using this one, I reference will be obtained in this voltage controller, and this one will be used to generate the VA references, which are being used to generate the PWM signals. So if you compare these two inverters, one is a power electronics based multi-level inverter, which we are calling is a static inverter. The other one is a rotary based inverter, DC motor coupled synchronous generator. If you see these performance indices, okay, so from the power quality point of view, if you see the static inverters, like which are power electronics based inverters, they have poor performance, whereas the rotary based machine based conversion, it is good. And moment of inertia, if you see, they have very negligible moment of inertia, whereas the real machines have high moment of inertia. And stability point of view, the real machines, they show high performance, whereas the static converters, they show low performance. Resiliency, low. In case of rotary, it is high. The frequency response is unstable. Voltage response is unstable in case of pulse based converters, whereas they have highly stable in case of rotary based conversion. So these are the performance indices point of view. If you compare it, the rotary based converters, they are showing good performance. From the operation point of view, if you see, life period is more for power transfer based converters as compared to this one. And power conversion efficiency is also more than 95%, but here it is lesser. System maintenance is low, which is good. And here the system maintenance requires high priority. Speed of response is higher, here it is moderate. Okay, from the operational point of view, the static converters, they show better performance. So, but whereas this one are lower performance as compared to the static converters. And general features point of view, if you see, the implementation cost. So the static converters, they show low implementation cost, and the space requirement also less for the given amount of power to be converted. Filter circuitry, that is one drawback here. You require high filter capacity, filter requirements, whereas this one is less here. Design complexity is low, but here it is high. Unit size is one of the important thing. Okay, it is very less here for the given amount of power to be converted. Acoustic noise is less, and it is applicable for all types of loads, because okay, so even 1 megawatt of power conversion typically requires a small 100 square feet capacity center. If it is there, that will be sufficient for conversion. Okay. So now if you look at these two things, okay, so for certain applications, certain things are good. For the performance indices point of view, rotary based conversions are good. From the operational point of view, the static converters are good. But from the general point of view, also these static converters are good. But we require both the features in a single converter. That's what we require. Okay. So the power trans based converters, they're lacking here. Okay. So then our aim, okay, so our research work point started from this point. Okay. So why not we have both the matrices being met in a single converter? Okay. So now apart from the power converter, the control system also plays an important role. Okay, so selection of the suitable architectures, converters, and controls. Okay, so these things play a major role in the microgrid's performance. Okay, so the proposed scheme is, okay, so this is a combination of both the things. Okay, so this is the conventional static converter, this is the conventional rotary converter. Our proposed method comes from these two architectures. Okay, so we have an inverter. So renewable energy sources being connected to the load through this inverter. Okay, so now we are in the closed loop control. So in the case of conventional thing, we have a cascaded droop voltage and current controls. But in our application, we have the models of the DC motor coupled synchronous generator. Okay, so its detailed diagram, if you see here. Okay, so this configuration, we'll call it as like closed loop virtual DC motor coupled synchronous generator based control scheme. So this we are calling it like CLV DC, closed loop virtual DC motor coupled synchronous generator scheme. So this is the typical control scheme. Okay, so here you can see like these are PV, wind, energy storage. Okay, so battery, fuel cells. Okay, so they have their own local controls, and they're all being connected to a common DC bus. Now we have a utility grid here, and local loads are there. So here this DC to AC conversion happens. Okay, so this is an inverter being fed to the AC bus through these filters. Okay, now the voltage and currents are being measured. Okay, so they do this ABC to DQ conversion. they are being fed to the excitation control to control the voltage of the output. And from the DC side also, the DC voltage are being measured. They are given as a input to the DC motor model, and any variation in the input side voltages, they directly have the impact on the torque being generated in this model. So now the generator model is having the torque input and the voltage input. So then based on this one, okay, the generator model will provide the theta M and the IABC. So this IABC or VABC, you can take it as output. So these forms the reference signals for the PWM generator. So which in turn will generate the PWM signals that are required for the three-phase inverter. So in this particular work, we have used a three-phase 5-level diode clamp multi-level inverter. So generally I'll call this one as a DC-MLI, DC diode clamp multi-level inverter. So a sine triangular PWM has been used. Okay, so in this one, 4 carrier signals, each with a carrier frequency of 1 kHz and an amplitude of 2.5. Total it will be 10. So the amplitude, the modulation signal has a frequency of 50 Hz and an amplitude of 10. So these two things are being compared and the signals are being generated for these diode clamp multi-level inverter. So the closed loop virtual DC motor. Okay, so this is the proposed closed loop virtual DC motor coupled synchronous generator scheme. Okay, so these are all models here. So this is the mathematical modeling of the DC shunt motor. So corresponding equations here you can see the PI1, PI controller 1, PI controller 2 are being used. Okay, so these are based on the generator speed and motor speed comparison. Okay, so IA reference is being generated. So by using PI controller 2, IA will be generated. So this generates the electromagnetic torque. So this is from the motor generator equations. Okay, so we generate these outputs. Okay, so this is the synchronous generator model. So here also we use some type of equations to calculate the VFD. Okay. So now this is the detailed signal routing. Okay, from the DC bus side we have DC bus voltage. From the AC bus side we have the AC bus voltage reference. AC bus voltage are being sensed. Okay, so and finally you have this IE reference ABC, which is being sent to the PWM signal generation. Okay, so now this DC motor model provides a controlled mechanical torque. Okay, so whenever there is a variation in the input side voltages or okay, so any frequency variations on the grid side, okay, so those will be sensed. Okay, so here the electromagnetic torque and mechanical torque, those things will be compared, which generates these. Okay, so theta SC. Okay, and the exciter model provides the controlled field voltage to the generator. So thus the frequency variations and the voltage variations are regulated over the uncertainties and thereby controls the I reference. Okay, so because this is being fed to the inverter to control the pulses. Okay, so which will vary the output of the inverter voltage and frequency. So thus this in turn controls the firing pulses of the inverter and injects the virtual inertia into the system. Okay, so because these Power-Electronics based converters, they lack the inertia, but by using this control system, okay, so we can inject the virtual inertia into the system. Okay, so these are some of the parameters that are used for simulation. So here we have used these DC motor, DC shunt motor model parameters and synchronous generator model parameters. Okay. So and also an experimental setup has been developed. Okay, so here we have used a PV being connected to load, and we have used a DSpace controller board DS1104, and this is used to generate the signals, and the closed loop control virtual closed loop virtual DC motor coupled synchronous generator model has been used in this controller board to generate the signals. Okay, so in this particular case there is no grid, so that's why this is an island mode of operation. So for normal operation we have used this part, but for fault cases and all. Okay, so to avoid the damage to these inverter switches and all. Okay, so we have not created the faults by using these experimental setup. So this is the specifications that are of the PV system and DSpace system and inverter systems. Okay. So this is another experimental setup. Okay. So in this particular case, instead of using a DSpace board, okay, we have tried with various types of controller cards. Okay, so one is DSpace, one is PCI card. Okay, so here a MATLAB Simulink based real-time toolbox. Okay, how we have used it. So so NIPCS 29 multifunction input-output DAC has been used. Okay, and we have an inverter module. Okay, so IGBT based three-phase two-level inverter. For experimental setup, okay, we have used two-level inverter. For simulation, we have used five-level inverter. Output monitoring scope, okay, and filters, capacitors, okay, and these are the current and voltage measuring devices. These are the loads, RL type of loads. So this is the test cases, okay, for the power quality analysis. Okay, so we have done the simulation as well as the experiment. So simulation, in the simulation we have verified the THD values, voltage imbalance values, over current and under voltage, over voltage and under voltages, frequency deviations. And in case of an experimental setup, so the frequency deviations to check it, okay, the single line to ground fault has been created in simulations, but that we have not done when it comes to the experimental to avoid the fault cases. Okay, so now here the base load is 250 kilowatt, but to check the THD, we have injected a dynamic three-phase load variation, okay, 0 to 30 kilowatt and 0 to 20 kilowatt. A combination of these things are being injected to these renewable energy based microgrid for testing the THD, for testing the voltage imbalance, reactive load, okay, load unbalance. Okay, so only on one phase, a 50 kVA load is being connected. Okay, so at a point 0.3 seconds. And over voltage and under voltage voltage to check it, we have switched on a large capacitor and inductive loads, okay, set to various intervals, and we observed how these voltages are being varied. And when it comes to the frequency deviation, okay, for simulations, we have created a single line to ground fault at microgrids bus and seen what is the frequency variations. And experimental reactive power load is being changed. Unbalanced loads are being varied on a phase. And so the signal shape under system unbalanced conditions, okay, so has been observed in case 6. Okay, so whenever you are doing this part, the signal shape also has been observed. So total 7 test cases have been done, and we'll see the results. Okay, so this is the simulation results. So you can see the THD from the diode clamped multi-level inverter based renewable energy microgrid, and this is from the closed loop virtual DC motor coupled with synchronous generator based thing. Okay, so the THDs are less. So this is the case when you are injecting the reactive load on only one phase, that is on phase A. In a three-phase system, we have A phase, B phase, C phase. Okay, on one phase, when it is being connected at 0.03 seconds, okay, and it is connected to grid at 0.06 seconds. Okay, 0.6 seconds. Okay, so now the voltage imbalance has been measured by using this equation. Negative sequence to the positive sequence ratio will be considered as voltage imbalance. Okay, this has been plotted. Okay, so initially it is the instant at which the load is being connected to the unbalanced load is loading is being created. and this is the instant at which it is connected to the grid. Okay, so generally we wanted to have this voltage imbalance should be as close to 0 as possible. So the green one is the diode clamped multi-level inverter, okay, which doesn't have any proposed method. This is a conventional method. So this is the DC motor coupled synchronous generator. This is a rotary based conversion. This is a static. The blue one is a static converter. This is a red dots, long dots is a rotary based conversion. This is the proposed converter. Okay, so here anyhow the voltage and balance are very close to 0 in all the cases. Whenever the moment you are connecting to the grid, okay, so it tries to reduce the voltage imbalance as compared to the other two schemes. Okay, so this is one of the advantage of the proposed method. So in this particular case also, so the microgrid voltage, okay, it should be very close to the unity. Okay, so if you see here, this is the red one is the proposed method. Okay, so the moment you turn on the large capacitive load, and here large capacitive load is turned off, here the large inductor load is turned on and turned off. So if you see this red color dot, it is little bit away from the one as compared to the other two cases. So similarly here also, so it tries to be close to 1, like the nominal requirement. Okay, so the ideal case. So this is the advantage of the proposed method as compared to the other conventionally available methods. So this is the frequency response test. Okay, so if you see here, a single line ground fault has been created at this location, and this is the instant where the fault is cleared. During these fault conditions, the blue one is the conventional static inverter. Okay, so the frequency variation is too much. Okay, so actually our frequency is very close to 50. Now it is touching 49.7 or something. But the rotary based inverter, the red color one, so this is also oscillating. Okay, so because the machine, the closed loop virtual DC motor control is mimic the behavior of the real machines. So that's why it is almost like equal to it is mimicking the behavior of the real machines. Okay, so now from this picture also we can say like, okay, so the proposed method, the real of the DC motor coupled synchronous generator in its closed loop, it is also behaving like a real machine. So these are the experimental results. Okay, so the THD is 15.81 in case of diode clamped multi-level inverter. In case of the proposed method, it is 7.72. So here the wave shape is being pictured. I think this is not shown here. Okay, so the wave shape of these diode clamped multi-level inverter is distorted, but here a little bit better voltage wave shape will be there. Okay, so I think here pictures are not being seen. So if you compare all these performance analysis, okay, so on the conventional as well as the proposed method, so for various test cases, the conventional DC diode clamped multi-level inverter, like static inverter, it failed in this voltage imbalance case. Even direct machine, real machine based also failed, but the proposed method, okay, so it is not violated in any of the cases, even under the, okay, so in experimental also. Okay, so from this one you can say like the proposed method is shown better results as compared to the other methods, okay, for various indices. Okay, so this is the method which we have started. Okay, so there are other various this type of control strategy, we'll call it as a virtual synchronous generation concept, because here you are injecting some type of inertia to the grid through the control logic. Okay, so similar type of things people they did it in literature, but their topology is different. Okay, so what are all the various schemes that are various frameworks that are available in literature? Okay, so there are some 4 types of topologies which are generally used to compare it. Okay, so this is a vSync project based virtual synchronous generation topology. This is a IEP, industrial electronics, electronics power electronics based virtual synchronous generation topology. This is a KHI's Kawasaki Heavy Industries Polytechnics, Kawasaki Heavy Industries Virtual Synchronous Generator Topology, and Issei's lab, Professor Issei from Osaka State University, he developed this virtual synchronous generator topology. Okay, if you see these things in detail, okay, so there are the vSync topology. This is a project. Okay, so in this one, the control logic and they use the control logic and the PLL. The PLL is a differential equations based phase lock loop. Okay, so it senses the grid voltage and generates the I reference, which in turn used to trigger the pulses. Okay, so and also they use the energy storage to mimic the dynamic behavior of the synchronous generator. Okay, so the limitations is like the dynamics of the synchronous generators are not considered. Okay, so in the virtual synchronous generator control loop design. So that's why this scheme cannot emulate the dynamic behavior of the synchronous generator, as its operation depends on the storage system's charging and discharging times, which are not analogous to the electrical machines. So the another one is IEP's topology. So here they use the synchronous machine model. So it takes the grid voltage, okay, and the proposed approach, it is developed based on the use of synchronous machine model in the Polytrans based voltage source inverter control loop. So here also it takes some inputs. Okay, so the input like mechanical torque and excitation voltage. So but the limitations are like they are assumed values. Okay, so which are constant and they may not cope up with the real-time disturbances. Okay, so because of that one, this will affect the efficacy of the control system, as it is difficult to maintain the frequency and voltage stability during disturbances. So this is another topology, Kawasaki Heavy Industries Limited based topology. So this topology is having 3 submodules. One is AVR control, governor control, and phase lock loop. Okay, phase lock loop based current generation. Okay, so the limitations here also, the reactive power input to the AVR and the active power input to the governor, which are assumed to be constant. Okay, so assumed values rather than practical values they have considered. And moreover, the variations of the powers with respect to the load variations or any other disturbance are not considered in these assumptions. So this scheme cannot cope up with the actual power varied by the load changes in the real time, so which impacts the performance of the overall control. So this is the Issei's lab, VSG based VSG topology. It is a swing equation based topology. Okay, so swing equation based control logic is being used in these control loop. So the limitations are like the assumed active power reference as well as the reactive power references for the synchronous machine operation, which affects the overall control system's effectiveness. Besides, the scheme retains the use of PI based controller methods for QV. So because of which, okay, so it leads to the when under the nonlinear conditions, okay, so the performance is degraded because the ineffectiveness of the it is ineffective for nonlinear disturbances and difficulty in PA against tuning, etc. are the drawbacks of this one. So we compared the proposed method with the literature. In literature, the IEP based VSG source based frameworks are generally used to compare. So that's why we also compared the proposed method with the IEP based VSG topology. Okay, so various cases have been considered here. Okay, so they are like balanced load variations, nonlinear based load variations. And normal load normal under so the balanced load variations, nonlinear load variations, they have done it for checking the performance indices in terms of wave shape voltage deviation, frequency response. And this is for the simulation studies, and this is for the experimental studies. Okay, so in this particular case, for total harmonic distortion, reactive load variation, resistive load variations have been considered. For voltage spike, the impedance load on will be done, and voltage imbalance cases, unbalanced reactive load, unbalanced resistive load variations have been considered. So the testing load has been done as per these time variations. Okay, so here electric arc furnace load has been turned on and turned off. Uh, Instantaneous flicker sensations have been created. Okay, electric load, arc furnace load has been connected and disconnected. Okay, so these are the things which have been tested to check the performance indices. So this is the comparison of the conventional IEPE and proposed method. Okay, so the top one is the IEPE based scheme's voltage response, and this is the proposed scheme's voltage response. So here you can see the spike is almost like the moment it is the instant which the leading load is being connected, the spike voltage gone up to 1350. So whereas here it is 1120. So this is the case where the electric arc furnace load is turned on. Okay, so here you can see like on conventional IEPE, so all the three-phase voltage are becoming zero, but here it is the dip is not much. And the moment electric arc furnace load is turned off, okay, so the restoration time is very close to, you will not observe any deviations, but here you can see that the restoration time for this one is almost like 2 cycles. And the voltage deviations, okay, so this is 4.9%. Here the voltage deviation is very less, 0.5%. And this is the instant where the electric arc load furnace is on and off. And this can be seen in a zoomed view. Okay, so here the frequency variation is more here, it is limited. So in this particular, when the arc furnace load is off, during that time also it is high, here it is low. So these are the experimental results. Okay, so this is the comparison for various cases. Okay, so the top one is for the IEPE based method, and the bottom ones are for the proposed method. So THD is 3.58%, here 1.85. So in this particular case, 7.98, 4.56, this is 9.74, this is 4.82. So in all the cases, the proposed method is showing better results. And the sag also, if you see, so here you can see the sag in the voltage is limited, but here it is almost 60%. So this is the voltage response. Okay, so the imbalance is 10.5, here it is 2.45. So single phase unbalance is there, here two phase unbalance is there, this is 7.79, this is 3.416. So if you summarize all these results in a tabular form, okay, so the red ones are the violations. So as per the standard, it should be limited to 800, but it is crossed 1120 in both the cases. It is, in this case, it is 1350. So here the voltage imbalance is 3%, here it is 3.16, little variation, but all other cases, the conventional IEP is also violated for many performance indices. But here you can see that, okay, for certain, only for voltage spike case, it is a little bit more, okay. Otherwise, it is very close to the standard limit. And these values are very much lesser as compared to the conventional IEP based methods. So the salient features of the proposed control scheme is like, okay, it mimics the behavior of the conventional electrical machines based power plant operation in microgrid. Due to the closed loop operation, the system can cope up and tolerate the real-time uncertainties described above. So the emulation of the dynamic behavior of the electrical machines improve the moment of inertia of the renewable energy based microgrids. This enhances the capability of the loads to stay connected with the local and the utility grid power supply during the uncertainties. So from these simulation and experimental results, we can clearly say like, okay, so under different operating conditions and disturbance conditions, the proposed scheme shows improved performance as compared to the already existing methods in the literature. So the improvement of the power quality offers greater opportunity to integrate energy-based microgrids with the utility. This helps in getting stable, continuous, and reliable power supply through the adherence to the various regulations of the regulations and standards. Okay, so with this one, okay, so the presentation is over. Okay, so any questions are there, then we can spend some time on that part.
Thank you, sir. Dear participants, if you have any questions, please ask, sir. Please unmute yourself and ask. Ravikiran, sir. If you are unable to unmute, please message in the chat box.
So I assume that, okay, at least some information has gone into your mind, and at least it is useful, I feel.
Yes, sir. It's very insightful information, actually.
So if there are no questions, then I will stop sharing the screen.
Dear participant, anyone have any question? No? Sir is waiting. Okay. Praveen sir, are you there?
Hello, sir.
Sir. Yes. Yes, Sugnakar, sir, please.
Sir, any suggestions to researchers regarding the microgrid charging station applications in future?
Okay. Okay. See, microgrid charging stations. Okay, so now one is the location. Okay, so where it has to be installed. Okay, so because the microgrid, when on the distribution side, whenever these charging stations are being connected, they are like the load is not permanent. Okay, so means whenever there is a EV is coming and being charged, during that time you will have load. So otherwise you will not have load. Okay, so what is the best place to check the EV charging location is one important thing. Okay, and also whenever this is being connected, okay, so how much, okay, whenever this EV charging is being placed, okay, so what are all the challenges are being faced by the distribution system. Okay, so this is some of the important aspects that needs to be considered, and in that direction some research people, they have to think it. Okay, so where is the location and how much amount of capacity to be connected. Okay, so that needs to be addressed.
Okay, sir. Thank you, sir.
Thank you, sir. Sir, and one more question from my side, sir. Actually, if we are going with island operation and V-grid, so how can we, this energy storage systems, leveraged to improve stability in
Yeah.
V-grids during island? So most
Yeah.
of the times we have instability in this
Yes,
situation. So how can we leverage?
See, actually, this is an important question. Okay, so the reason is the energy storage acts very fast as compared to the renewable energy sources. Okay, so that's why if you see some of the topologies, okay, the energy source is one of the important thing. Okay, whenever this control logic is being used, if it is connected to the energy storage, the performance is better as compared to the directly when you are using a PV or wind. Okay, so because this PV and wind, they are intermittent. Okay, so they continuously they change their output depends on the available input like irradiation or the wind velocity. So these things continuously change. Okay, so if you have a proper the selection of these battery energy storage system is also an important thing. Okay, so the battery energy storage, optimal battery energy storage is an important when these renewable energy sources are being connected. So your question is can you repeat the question once again, ma'am?
Yes, sir. So how can we leverage to improve the stability?
Yes. Definitely these So definitely the energy storage systems will help in adjusting the reliable input from these microgrid. Okay, so because these PV and wind, when they are changing their outputs, okay, so the V grid side, it will further worsen the condition. Okay, so if the proper P and Q are not being injected to the grid, okay, they further worsen the V grid. So whenever these battery energy storage systems are there, you can have a smooth control on the output. Okay, so that will leverage the performance of the microgrid. Yes.
Okay, sir. Thank you, sir. Still, any participants, you have any questions?
Samyukta ma'am will ask one question to sir.
Sir,
Sir, nowadays AML is playing a major role. So how it can go to assist to the grid so that it controls the weaker grids? How is it? Any best mechanism or system is there, sir?
Yes. See, the power electronics based voltage source inverters, they depend on the PI based controls. Okay, so there the PI based controls mostly they are linear in nature. Okay, so whenever there is a non-linear control is there, during that time the AI based things they play a major role. Okay, so when you see the conventional static inverter, there is a droop control. Okay, so the droop controls are majorly like a PI based controls. Okay, so again there these the AML based methods they work better. Okay, so even we did some studies on these fuzzy logic based droop controllers to improve the performance. So there is a lot of scope for these AML based applications for these control loops. Apart from that one, the AML applications for the load variations and the solar radiation variations to predict it, like forecasting applications, these AML methods are much useful.
Okay, sir. Any questions
Sir?
from audience? Yeah, sir, please.
Sir, in EV charging, so generally we are using grid to vehicle charging.
Grid to vehicle.
Suppose if you go with the vehicle to grid,
Yes.
so is there any latest methods to synchronize the voltage and frequency of the grid when we are transferring the power from vehicle to grid?
Yes. See, majorly this can be discussed depending on the size of the power that you are going to inject to the grid. Suppose if it is a single EV, okay, so the power output from its own battery is very limited. Okay, so that will not impact the grid's voltage and frequency much. Suppose if you have a bulk, so many EVs are being connected to a local charging station. Okay, so they will impact the voltage performance. Okay, because frequency. So generally these things are connected at the distribution side. Okay, the distribution side, power variations, they majorly impact the voltage as compared to the frequency. Okay, so whenever these vehicle to grid or grid to vehicle, so whenever it is a grid to vehicle, they draw the power. Whenever you have a vehicle to grid, they inject the power to the grid. Okay, so whenever you are drawing a power from the grid, there is a voltage drop will be there. Whenever you are injecting a power to the grid, so the voltage improvement will be there. Okay, so the voltage variations, so as long as they are well within the limits, no issue. Hope it clarifies your question, or if you still not convinced, okay, you can repeat the question once again.
Yes, sir. Okay, sir.
Yeah.
Thank you, sir.
Thank you.
Still, anybody have any questions, sir? Okay. Sir, thank you very much, sir, Dr. Ravi Kumar, sir, for explaining theoretically and experimentally with proofs all regarding about your topic, and also you have clarified our participants' doubts also, sir. Thank you, my sir. Thank you, Mr. for giving the good explanation for us. Thank you, sir. Thank you very much.
Ravi sir, from my side also, thank you so much, sir.
Thank you, ma'am. Thank you. Yeah.
I troubled you a lot.
Yeah, no
Even
issue, no
your
issue. Because
even your busy schedule, you accepted my invitation and this evening time, and you have
with the
delivered a great
participants,
session.
okay, again to address these participants, I have to change my explanation. So only from that point of view, I was a little bit worried. But otherwise, see, even now also people from your side also they are asking many questions. Means they are trying to understand the concepts of the electrical side. Okay, so that is one thing which is promising and feels we are very happy when people they ask questions and if you are trying to answer those things. So very happy to see the participant side also some support. Yeah. So
Thank you, sir. Thank you
thank
so
you,
much.
thank you. So I will leave the call now. Yeah.
Yes, sir. Thank you, sir. Thank you.
Thank you,
Thank you, sir.
thank you, thank you, sir. Yeah.
Thank you, sir.
Yeah. So go ahead, sir. Can I start for the second session speaker introduction?
Sir, can you share the sir mail ID for future contact?
Yes, sir. We'll share, sir. After FDP, we'll share. At the end of the FDP, we'll share, sir.
Okay.
So I'm handovering session to next moderator. Please introduce the next speaker.
Yeah. Thank you,
Feedback
madam.
from sir.
Feedback from my captain chat box, sir. Good to see that.
Praveen sir, we missed the screenshot of speaker,
Feedback
sir.
form is not there,
I have
sir.
taken
Only
one.
attendance sheet is given.
Yes. Okay.
I have
Okay,
taken
sir.
the screenshots, madam.
Okay. Okay, sir. Done. So please
Okay.
introduce second speaker.
Yeah,
sir.
yeah. Okay, thank you, madam. So I'm eagerly waiting for introducing Dr. M. Raju, sir. Sir, welcome, sir. So I am K. Praveen. I want to introduce Dr. M. Raju, sir. M. Raju, sir, is obtained his BTech in Electrical and Electronics Engineering from JNTU College of Engineering, Karimnagar in 2012. He was awarded with PhD from National Institute of Technology, Silchar in December 2018. He joined Maturi Venkata Subbarao MVSR Engineering College, Hyderabad as an assistant professor and served there from 25th February 2019 to 23rd November 2019. Later, he joined in National Institute of Technology, Tiruchirappalli as a postdoctoral fellow as a PDF from 28th November 2019 to 16th March 2020. Currently, Dr. M. Raju working as an assistant professor in electrical department at Maulana Azad National Institute of Technology, Bhopal, from March 2020. He has authored various journal and conference publications of international reputed. He has a patent in his credit and he received 2 Best Paper Presentation awards. His areas of interest are including conventional and deregulated automatic generation control or load frequency control, optimization techniques, soft computing techniques, mathematical modeling of electrical energy systems, applications of machine learning and blockchain applications to smart grid systems, etc. Now I welcome sir. Please take over the session, Dr. M. Raju sir.
Raju,
Hello.
sir? Yes, sir.
Madam, good evening, madam.
Good evening, sir.
Good evening, all the faculty members as well as participants.
Yeah.
So thank you very much for introducing me. So let me share my PPT. So start presentation. Now I hope you can see the PPT.
Yes, sir.
Yes, sir.
It's visible,
Yes, sir.
sir.
Visible. Yeah, it is visible, sir.
Please full screen mode, sir. Keep full screen.
Please, just a second. So good evening once again, all of you. So today I will talk about something on how the secondary controller in the power system, especially for the regulation of this frequency problem when the load demand changes in the power system, especially. So this problem, all of you may be knowing that automatic generation control problem. When the load demand on the power system increases, it is expected that the generation should also match with the in accordance with the load demand in the power system. That problem is basically called as automatic generation control problem. And this is also called as load frequency control problem and automatic load frequency control problems. So you may be having some idea of the AGC problem, that is automatic generation control problem, which is also called as LFC problem, load frequency control problem. As load changes, you know that frequency on the system changes. So it is also called as load frequency control problem. So in the scenario of this continuous load changing, especially with the incorporation of different kinds of loads, sometimes we may be unaware that how the load on the system varies in a particular time. So in that, how to control the frequency of the given power system. So for that, basically we go for secondary controller design. So how to use the effective secondary controller design by using the AI techniques. Basically, those are called as some optimization methods like genetic algorithm, particle swarm optimization. We'll discuss some basic thing and I will give some ideas how to implement for further studies. Okay, so let us move into the topic. So this is the standard IEEE definition. You can see that if you're having the screens visible, just try to read the definition. So the regulation of power output of electrical generators within the prescribed area in response to changes in system frequency, tie line loading, or the relation of these two or these to each other as to maintain the scheduled system frequency and or the established interchange with other areas within predefined limits. Means basically this sentence say about, so this is in the event of any load changing, the event of any load change, the frequency as well as tie line loading in the particular areas, interconnected areas. Area means what? We assume that area means this is not a geographical area. Area means it is a power system area. Power system area defines in such a way that the frequency of that particular portion or the part of power system is constant or same. That is treated as one area. Such areas, if they are interconnected by means of transmission lines with one another, that system is called as an interconnected system. So in these interconnected systems, you may be having tie lines, because interconnection will be possible through the tie lines only. That is, those are also called as transmission lines. So transmission line should not be overloaded. Means the interchange or the exchange of power between the predefined between the areas must be there within the predefined limits. As well as the load changes, it is expected to have the frequency constant. So this is what the IEEE standard definition says. So that only I have written here. You see here, this one. Whenever the load demand of a control area changes, it shows the adverse effect on the system steady state operating point, that is frequency, that may lead to outages of generation, causing the mismatch frequency and tie line power flows. So then AGC will come into the picture to make this balance, that the load as well as the power generation. So load and generation, load as well as the frequency matching. So the name AGC, automatic generation control, or LFC, load frequency control. Okay, so I hope you got some idea about AGC. So the you know that when the load on the power system increases, we'll see now, we'll see through the simulation results, when the load on the system increases considerably, if the load on the system increases, so the frequency will be fluctuating much more. So to have the minimum fluctuation of frequency, because it is required to have the almost constant frequency to operate the power system in a safe way. So what we do is, in addition to our primary control mechanism, we will go for the secondary controller. So primary controller mechanism is provided by the governor of the given turbine. But with the governor of the given power plant, maybe thermal or hydro power plant, you may not be getting the frequency variation to 0. But if we select the secondary controller, then it is quite possible to have the 0 frequency deviation. So we'll see that. We'll see in a shorter while in the lecture itself what is the impact of this secondary controller, and what will happen if there is no secondary controller. That also we'll see. So see that some authors, they have studied this particular problem in the single area system, and you can see here, see my cursor there, some those have studied with the interconnected system. Okay, so basically in previous days, the control problem, that is automatic generation control problem, was studied with the thermal and hydro power plants, because those are the major contributors of the load demand. They will be supplying more amount of power. Similarly, that to maintain the system voltage, so we have one more term, that is automatic voltage regulator. So combined frequency as well as voltage problem formulation is also possible. Okay, some various authors have studied various things to control this particular voltage as well as frequency on the synchronous generator part, that is at the generation level. Okay, so see that the importance of secondary controller. So primary controller is what your governor of the given generating plant, but by making use of secondary controller basically that will be of I controller, that is integral, PI controllers we use, and PID. Basically we use these controllers, and some advanced controls also there that we'll see in the upcoming slides. So what is the function of this secondary controller? So the secondary controller used in AGC plays an important role that bring back the steady state error present in the power system outputs, that is power system frequency as well as tie line powers. So just now I have already said, whenever if you go only with the governor part of the given turbine or generating station, there exists some steady state error, which is undesired as an electrical engineer point of view. So then we could go for some kind of mechanism that is called as secondary control mechanism or automatic generation control mechanism. So if you see that the governor action, if you compared with the secondary control action, that is governor is very fast. So that's why the order of the governor we take in the seconds. Whereas the secondary controller response is somewhat slow. Means after occurrence of the primary governor mechanism, it is expected to have the secondary control action. So hence it is slow in nature, and time constant of the secondary controllers we take in the orders of some minutes. Okay. So see here, this one you see the primary governor mechanism, control mechanism alone is not sufficient to suppress the oscillations and requires for suitable secondary controllers. Means the primary control mechanism is not that much efficient. It will give the instantaneous action in the orders of seconds, but it will not suppress or it will not take out the steady state error present in the frequency or tie line errors, tie line variations. Hence we should go for the another control mechanism that is called as secondary control mechanism. Hence the secondary controller plays an important role in the power system operation point of view. So in that you see that some authors, they have used the IPI and the PID controllers. Even some authors, they have used some fractional order controllers. We'll see what I mean by fractional order controllers and what is the structure of these controllers in the upcoming slides. Okay, so see that controller, if you are placing means, so suppose if I have placed I controller, what do you mean by I controller? So Ki by S, its transfer function, its value is how much? Ki by S, where Ki represents integral gain. Suppose if I am going for PI controller, the controller parameters are Kp and Ki. Okay, na? So the gains are the parameters of this controllers must be selected properly. Okay, na? So selection is also important for the effective minimization or the suppression of the oscillations. And also after selecting the secondary controller, so how we have to select the gains or the parameters of that particular controllers. So to select those gains, we go for the optimization techniques. Basically, that is some kind of genetic algorithm. You may be all having some kind of idea, particle swarm optimization, and so on. So many algorithms are there. So based upon the efficiency of the algorithm to fit for this particular problem, that is to tune the controllers that in turn effectively control the oscillations in the power system. So for that, we should require an efficient controller with optimized properly. So we'll see all these things slowly we'll understand. So see that. So as we have discussed, secondary control is important. Also, the secondary controller parameters choosing also is very important. So that see, some authors, they have done PSO, that is particle swarm optimization, and they have some authors have utilized genetic algorithm, and they have hybridized these genetic as well as some other algorithm, that is simulated annealing algorithm. Okay, that is the main motto of the given AGC problem. So till now we saw that the control area, in the control area, the oscillations in the frequency as well as tie-line powers must be maintained within the prescribed limits. Okay, so for that, what we are doing, we are, in addition to primary control action, that is governor mechanism, we want to keep a secondary controller. So for the secondary controller, not only the secondary controller choosing is important, but also the tuning of its variables. Those are basically gains of the controller is also important.
These are some of the scenarios. I'm not saying that everybody is doing.
So for that, we basically go for the optimization techniques. So some of the optimization techniques that you can see already in the slide. So based upon the discussion above, so we'll in today's presentation, we'll develop some single area system as well as some isolated area system with the thermal and hydro generations, and we can incorporate that one, the RES into that. So we'll see that. And we'll also see the effect on the system variables with the secondary controllers as well as without secondary controllers. Okay, na? And we'll compare the both results. Okay, na? So we'll see the performance of various secondary controllers also. We'll take some integral, proportional integral, and proportional integral derivative controller that we'll see. Okay, na? So first we see that. So if we this one first you observe carefully. So this is what your thermal power plant. So figure A, you observe figure 1A. So figure that 1A. So in that we are having the mathematical modeling of the given thermal power plant without any controller. Without any control. See that. So the load is modeled here in the power system. So the generator side modeling, that is governor, turbine, all the things are modeled in the left side. So 1 by R represents the governor regulation parameter. So we are having some kind of the mathematical modeling for the all parts of the given power system. And this is what your small signal modeling. Small signal modeling in the sense that is applicable for your small perturbations. Means small in the sense that small disturbances. So SLP means, see here, step load disturbance. SLP means step load disturbance. So this one A, if figure 1A, we are not having any controller, this is treated as without controller. Figure B, you see that 1B. So we have taken I controller, Ki by S. Just to remember, this is the load demand. SLP means step load perturbance. Perturbance in the sense that is a disturbance. Suppose the SLP is 1%, means whatever the total generation is there. Suppose if it is the thermal power plant is generating, you assume 100 megawatts of power. 100 megawatts of power. So 1% means 1% of that particular generation. That is 1 megawatt. Disturbance will be given. So like that, the study will progress. So here in this system, we compare with the performance of the given controllers, mainly I, PI, and PID controllers. And we will also see the interconnected system performance without secondary controller, with secondary controller, how the system is performing for the various controllers. That also we'll see. So the power system transfer function is this one, Kp by 1 plus STP, that is single order transfer function. Similarly, turbine part 1 plus STT, and governor part 1 by 1 plus STT. They are having STG. They are having the constants which are already suggested by the IEEE. Hence, if we take these two simulation models, and if you do the simulation analysis, okay, suppose say, so you see that, so this kind of response you will get. So where you have to catch the response is this one. So the output of power system, basically, we are having the mathematical proofs. I have not shown. See, this output after power system, the output is called as delta F, means change in the frequency of that particular area. So as it is isolated power system, so it is not connected with any other area through the transmission line or tie line. Hence, it is called as an isolated area or single area power system. So this is without secondary controller, as control is not there. This is with secondary controller. Okay. So the response for this particular system, thermal system, without any secondary controller. So that is basically for figure A. Figure A. So this one you see that. So what I have told, the output is delta F, means change in the frequency. Change in the frequency, how much it should be there. So after the disturbance occurrence, the expected value of frequency after some time is 50 Hz. Means the variations in the frequency is must be how much? 0. So see that, see my cursor, 0 is here, and we are having some kind of negative value. Okay, na? So when the load demand increases, frequency dips, means it is not going to settle after some time. So it is expected to settle after taking the oscillations following the disturbance in the power system. So this is not happening. So that's why we will go for the secondary controller, and we'll design the secondary controller. Okay, na? So
వచ్చేవాడికి అప్పుడు మీ సిస్టర్ చెప్తే రన్ అయింది. నేను మీ సిస్టర్ మా సిస్టర్ చెప్తే కంపల్సరీ వచ్చేవాడిని.
yes, please request to all participants, please mute yourself. So see that. So for the sake of the controllers, so as I already told you, here we are using the I controller. So I controller, so we can go for PI controller, PID. So this is the structure of various controllers. This is the structure of various controllers. Ki by S, transfer function. integral controller transfer function, PI controller, Kp plus Ki. In addition to I, we are having the proportional gain also, and the PID, Kp plus Ki by S into Kd into that n by 1 plus n by S, where n represents whatever filter coefficient. So this is what your secondary controllers. Okay, system first one, this one. This is which is not interconnected. This is isolated power system. So in figure 2, we are having the interconnected power system. So see that one first, figure 1A. 1A is both are thermal systems in both the areas, 2-area system. This is a 2-area system. So in this way, they will be interconnected. So see that what my assumption is, I'm assuming that the system capacities ratio is 1:1. Means if the first area is providing or producing the 500 megawatts, you assume, it is expected that second area also is to produce 500 megawatts. So then this A12, that is area ratio factor, area capacity ratio factor, that will become -1. Means that is equals to whatever the ratio of the given areas capacities, that is A2 divided by A1. Means area 2 capacity divided by area 1 capacity. That is a ratio basically. So in this case, that will become 1. So because I am assuming the 1:1 ratio, means the whatever the generation is there in the area 1, same will be there for area 2. And one more thing, that perturbation, that is disturbance, 1% I have assumed. Okay, in both the areas, if you want, you can assume this is 1. See that 1% SLP, 1% SLP. So here for the simulation studies, I have assumed 1% disturbance in area 1 only. Area 2, we don't have any disturbances. Okay, so that is the system. So this one, if you observe, both are thermal systems. Both are thermal systems. That is figure 2A. Figure 2C, you see that C figure, you see both areas are thermal systems only, but they are having whatever secondary controllers, respective secondary controllers in both the areas. They are having the respective secondary controllers. So this one, this figure basically, it represents the hydro governor, hydro system. This represents the hydro system. So figure 2B and 2D, they represent the interconnected hydrothermal systems. So similarly, as like in figure 2A, we don't have any controller here also in figure 2B. And figure 2D, it represents the controller part. Okay, so if you observe here, the hydro turbine is of, we can see that minus S into TWS plus 1. So TW stands for your water time constant. So basically that will be taken as 1 second. So this is the electric governor, the transfer function. Okay, so if you observe the hydro turbine part, in hydro turbine, in the numerator, if you observe that zero of that particular transfer function of the hydro turbine lies in the right half of S plane. Lies in the right half of S plane. So the that mainly forms whatever non-minimum phase system. So the controlling of this non-minimum phase system is somewhat complicated. Means whenever if you are traveling or if you are doing research on the higher order systems or the mix of various generating power plants, So the controlling will become complex. Now, if you are having only thermal and hydro systems, but in practice, so thermal and hydro systems in different areas. In first area, you have assumed thermal system, and second area, you have assumed hydro systems. But in practice, in the same area, all the generators are expected to be there, present there. Thermal generation will be there, hydro will be there, and we'll be having solar PV will be there, wind will be there, and sometimes we'll be having that geothermal power plants will be there, maybe there, and this small hydropower plants may be there. If we are going for ocean energy, that is tidal sources or wave energy sources may be there, and biomass sources also there. So all these generations, if they are interconnected for the particular area, we here only one generation I have shown, that is thermal system. So whatever I have said, so if all are there, suppose you may be having some kind of fuel cell generation, so the system will become more complicated, complex. So in that event, these controllers may not perform very well. So they may be requiring the other controllers like fuzzy logic controllers, neural network controllers, as well as this, as it is a multi-process system, you may be requiring the cascade controller system and fractional order controller system, because they will be having the more number of tunable parameters when compared with the conventional I and PI controllers. Hence, their performance is expected to be superior when compared to these controllers, I and PI, PID controllers. Okay, so this is the main important thing that you have to observe. So what will happen, how the controlling will be done in the event of the multi-source systems or generations that are present in the particular area. So in the same way, you may be having some kind of idea about the Indian power sector scenario. Previously, before 1990s, Indian power sector was the combination that is of isolated 5 regional grids. So we used to have the 5 regional grids. Those are operating independently. So at that time, so the 5 regional grids, maybe some of you are having idea that Eastern grid was there, Western grid, Northern grid, Northeastern grid, and Southern grid. So in the year 2013, December 31st, so the interconnection of the Southern grid. So previously, they have done interconnection of 4 grids slowly from 1991 onwards. So that all grids were interconnected up to on 31st December 2013, if I'm not wrong, 13 or 12. So on that day, so all the regional grids were they were interconnected, and we have achieved one nation, one frequency. Okay, na? So one nation, one grid, and one frequency concept. So this particular problem, whatever we are discussing, will lies with the interest of power system operation engineer. So how you have to tackle the situations with the, as you know that if you incorporate the renewable energy sources, so as they are providing the intermittent energy supply to the grid, so how to control them? So one of the mitigation technology to have that is to have more energy storage systems. So quickly they can dump the or give the release the extra amount of energy whenever requirement is there. And when the load is in normal condition, those energy storage systems will charge, and vice versa. When the load demand increases and when the grid is unable to supply those extra demands, these energy sources, energy storage systems, they may be battery energy storage system, and superconducting magnetic energy storage systems, and so on. Ultra capacitors, they're having different kinds of technologies. So they will be acting quickly as compared with your primary control mechanism, that is governor as well as secondary control action. But these primary as well as secondary controller action mechanisms that are inherently required. So without that, the steady state error in the frequency deviation will exist. So for that reason only, we are going for various controllers like integral, PI controller, PID controller, and so on. Okay, so I think you have got some idea. So here I will be explaining that simple particle swarm optimization technique, whatever you may be having some idea about that. So it was proposed by Kennedy and Eberhard. So the various steps you see that first will define the control parameters. If you are looking for any optimization technique, so we have to go for the its parameters. First, algorithm will run with some steps. So actually, basically, what is this algorithm? So algorithm is nothing but, that is AI technique is nothing but the formulation of the natural process in terms of some programming language, or you say in terms of mathematics, and to achieve the desired response from that. So what is our desired response? So the deviation of frequency as well as deviations in the frequency and terrain powers must be minimum. How it will be achieved? By using the effective secondary controller. So what do you mean by effective secondary controller? The gains must be suitable for all loading conditions. We'll see now. We'll see. First, let us understand this particular algorithm. So whatever the algorithm is there, that is having some kind of mathematical expressions. So in that mathematical expressions, you will be having some kind of variables that needs to be predefined. So in this particular algorithm, so you will be having the parameters such as learning rates. So if you see that the velocity of these particles, so this is particle swarm optimization, means that is basically inspired by the group of particles or birds, how they will search for food. Okay, so while searching for something food, so they have to travel to some kind of another place. So then when they are traveling with some kind of to some kind of place, so their position must be changed, as well as they should travel with some speed or velocity. So as we know that our problem is we are assuming optimization technique, we try to get the result as early as possible. So we go for the velocity rather than the distance, because velocity will be there in the straight line path. Means we assume like that. Okay, now from step to step. So here the parameters are, so see that, so W, that is called as inertial weight. That is called as inertial weight. Next, we are having learning rates C1 and C2. C1 and C2. Okay, now. So, and R1 and R2, random values. R1 and R2 are randomly taken between 0 to 1 to have the more exploration of the given search space. So after updating the velocity of all particles, then we will update their velocities, positions, sorry. So by making use of this particular expressions, we will update the position as well as the velocity. So how we will do, I will explain. First, we will initialize the control parameters. So R1, R2, in between 0 and 1 you initialize, and C1 and C2, those are called as learning rates. Okay, na? Learning rates. So we'll come to that, what do you mean by learning rates? Okay. And number of, suppose say, up to how much duration, or what is the termination criteria, or at what condition you are going to stop this optimization technique. So that is called as iterations. So up to how many iterations you want to run this particular program, or the termination criteria may be two types. Basically, you see that how many times this program should run. That is what your termination criteria, that is in terms of iterations. Second one is, if the output function value is not changing that much between the consecutive iterations, so that will see the previous iteration value of that particular function and the present iteration value. And if the improvement is not there that much, the program automatically stops. So that is also one of the termination criteria you can choose. Okay. Na? First, for every particle, what we will do is, we will initialize randomly the velocity as well as position vectors. Suppose say, as it is particle swarm optimization, so what it has to do, it has to find either minimum value or maximum value for the given problem. So what we will do is, so 5 particles you assume. So population size is how much? Our assumption is 5. You can assume anything. So for that 5 particles, you individually initialize these vectors, initial vectors, velocity as well as position vectors. So for the all particles, you initialize the position as well as velocity vector. And then by the available value. So in the first iteration, that is starting iteration, this PB is what your position best in that particular iteration. G best means, suppose if you have done 2 to 3 iterations, whatever the position is there for the particle, what is the best position, that position will be replaced here. So first you will initialize 5 velocities randomly and 5 positions randomly. So V vector defined, X vector defined. Now for the each and every particles, so now, so Vi means, suppose say first particle V1, second particle V2, V1, V2, V3. For the first iteration, we will again calculate the 5 velocity vectors. Again, 5 values of that particular particles will come. So now for each position, suppose say X1, X2, X3, X4, all 5 matrix you are having already. Those values you add with the corresponding velocity. First position will be added with the first velocity. Second position will be added with second velocity. So you will update that particular position. Now position has been updated. And again, for the second iteration, okay, na? First iteration with the given values you have updated. Second iteration, again you got these values, X values. You keep X values here. Okay, na? So like that, the process will keep on going. So after having the X values at the end of each iteration, you are going to calculate the fitness. So with the first particle, how much fitness is there? With the second particle, how much fitness is there? With the third particle, how much fitness is there? So if you will compare the fitness of this initial particles with the updated fitness, so that best fitness among these 2 iterations is called as global best fitness. That corresponds to position is called as global best position. That position you have to keep here. You may be not understanding in the starting portion, but if you do the one mathematical exercise, definitely you are going to understand. Nothing is there. How many particles you assume? Those many particles, velocities and positions first you define. So after defining those velocities and position, by making use of them, calculate the updated velocity and similarly updated position. Okay. And with this updated position, calculate the fitness function f of x. This should be done for each and every iteration. So each and every iteration, f of x must be calculated. In that way, the up to number of iterations you have to keep on doing. Or if you see the fitness value or the objective function of the system does not vary in the successive iteration parts, then you can neglect that or you can stop that particular algorithm. Okay. So this particular algorithm will do everything for you. Okay. So this is something about the particle swarm optimization. So you see that these are the controller parameters. Population size here I have taken as 100 and iterations I have taken as population size I have taken 10 and iterations I have taken as 100. So the common practice for this particular controller gains to keep them between 0 and 1 and the filter coefficient is of between 0 to 100. Okay, so that is what the minimum limits and maximum limits for various controller gains, that is integral Ki, proportional Kp, and differential Kd, as well as other parameters, whatever filter coefficient. So if you do this with this particular PSO, so these are the controller values that already we have seen. So see that. So figure 6, you see that when the system is compared, so PID controller. So if you see for thermal system, so these are the controller gains that we got. I controller gain is 0.4176. PI controller, that is 1, and other. These are the controller gains that we got in the. If you see that the comparison of the performance of various controllers for the 2-area system. Okay, so for this is for single area system. Single area system for because we are having only one area. If you see that, so it is expected to have the 0 frequency deviation after the disturbance. So see that after the disturbance, all controllers are trying to make the response to 0, unlike in the previous condition. Previous case, we saw that there exists some kind of steady state error. So if there is no secondary controller, we are having the steady state error. But if we are having the secondary controller, the steady state error is going to vanish. And one more thing is, so the oscillations or the deviations are in the frequency must be minimum. As an electrical engineer point of view, it is expected to have minimum values. Okay, na? So now if you see that black color response in that big picture, that is magnified here. So see that minimum value, that is under value and overshoot value, undershoot and overshoot values are very lesser when compared with the red color arrow. You see that PI controller as well as integral controller, blue one. So in this way, as the controller parameters are changing or increasing in nature, so the controller tries to more effectively mitigate the system oscillations. Okay, now for that we should require the some good optimization technique to handle the system oscillations. So see that if you compare the settling times, so settling times here you see that for PID control it is taking only more than 10 seconds, 10.88 seconds, 10.78, and PI controller is taking 27 seconds, and I controllers they are taking this is I controller is taking much more, so it is somewhat misvalue we have written, maybe it is 19 and so on. And also you see that peak overshoot values also very lesser for the PID controllers. So you see that the convergence curve we observe. Convergence curve means so how the function value is coming over the period of iterations. Okay, if you observe for iteration 50 to 100, so the algorithm is almost providing the same amount of cost function. There is no such evident improvement in the cost function value, that is f of x value. We'll see now what I mean by f of x value in that particular condition. So that this cost value is not changing beyond 50 iterations. Hence, to run the program in the minimum period amount of time and to reduce the burden on CPU, you can restrict the program to run only for 50 iterations. So first what you will do, you will run the program for various iterations and you will see where the program is going to have the minimum amount of deviations in the cost function value, so that you will take the as a reference. In this case, after 50 it is not changing that much, so take 50 as reference and run the remaining controllers with this particular 50 only. Okay, so this is best controller, the convergence characteristics. So if you see that, so see the equation 1. So suppose a system is interconnected, and what are the possible power system outputs in that? Suppose two areas are there means in one area we are having frequency 1, variation in frequency 1, another area frequency in area 2. As they are connected with the tie line powers, the tie line power variation also will come into the picture. So what should be our objective function now? The combination of these three must be minimum or maximum? Minimum. So the variations in the frequencies, interconnected areas frequencies, and tie line power combinations, or the summation, must be as minimum as possible. So that's why the f of x in this case is, I am taking as delta f1 square plus delta f2 square and delta p square. Why I am taking square? Suppose as the error is, suppose say 0.01 you assume. So that is does not having any significance in the operation. So we don't want that. We don't want to minimize such condition, maximize such condition. If we square 0.001, what will happen? That will become further smaller. So this particular cost function is neglecting the smaller variations, which are basically undesired. And another thing is that we may be having the combination of positive and negative values. So integration means, suppose basically you are adding the entire area over the simulation time for the simulator. So if you take positive and negative values, suppose say area is -3, somewhere come, you assume +3, somewhere come, +4, -4. Means if you add this plus and minus, the effectiveness of the given algorithm may go, because plus and minus will get cancelled if you simply add. So that's why if you take the square of -3 square, it will become +9 only, just like your the 3 square. Hence, all the errors, maybe positive or negative errors in the optimization problem will be considered. So that is the reason why I have taken the integral squared error. That is, this particular function is called as integral squared error. Integral squared error, ISE. You can go for another error, that is integral absolute error. Integral absolute error. Instead of taking the square value, just you take the modulus of given f and as well as the tie line power variations. So that is also one kind of objective function possible. And another objective function is weighted time t into this particular everything. That is called as ITSE, integral time squared error, ITAE, integral time absolute error. When these are possible, the cost functions that are possible for the objective functions. Okay, so this is what the convergence curve and cost comparison, whatever we have seen, that is f of x for the system, single area system, PID controller, if you see that, which is providing very minimum amount of cost function. So do we require a minimum value of cost function or a higher value of cost function? We require basically the minimum value of cost function because that was written in terms of errors. So error must be minimized in nature. So in this case, I controller is performing better. So similarly, you see that if you consider an interconnected system, that is a two-area system. So here, two-area thermal system, two-area hydrothermal system. So first, if you see the two-area thermal system, so two-area thermal system means this one, C, figure 2C. This one. In this, if we apply the particle swarm optimization technique with I controller, these are the values you get in area 1 and area 2, because I control, if you're putting means both areas, you can put I and I. Similarly, if you take PI controller in both areas, these are the obtained optimum values. And PID, if you are taking, these are the obtained optimum values. And if you see the response of figure frequency in area 2, I have not shown all the responses, figure 2 response, if you see that. So here also PID controller is providing the better responses when compared with the I and PI controller in view of all, that is overshoot, undershoot, as well as settling time. Okay, na? So F1 you see here, F1 I have shown here, and tie line power also, which is having smoother response when compared with the with PID controller when compared with the I and PI controllers. So these are the convergence characteristics. You see that cost of the f of x of the PID controller is quite low when compared with the integral and PI controllers. I and PI controllers are almost having the same cost function value, and PID controller is having considerable amount of depreciation, that is minimization in the cost function value, which is desired in nature. Cost function minimum value means the oscillations in the frequency and tie line powers is less. So that is what we required. And similarly, if you take the hydrothermal system, these are the values that you can get after optimizing use the PID controllers in the different areas. Same, the comparison that you see that. So here also PID outperforms the I and PI controllers in view of it may be settling time, it may be over and undershoots, and so on, or the magnitude of oscillations. You can observe that. Okay, so oscillations minimization we are going to compare. So here also you see that I and PI controller almost they are providing the same cost function, but PID is providing minimum cost function when compared with the I and PID control. This is what your cost function comparison for thermal and hydro systems by considering I integral, PI proportional integral, and PID proportional integral derivative controllers. So in which the PID controllers shows an efficient performance with the given system. So before concluding, you see that, so this is the discussion only pertaining to the thermal and hydrothermal system. Okay, when the two areas interconnected with the thermal and in one of the areas thermal and in one of the areas is hydro. So that up to that only I have shown, and whatever the algorithm also shown is of basic algorithm. So you can choose the various improvements in it. So like so when the system is having only the renewable energy sources in like just microgrids, so you can model the microgrid elements also. So same combination study if the microgrids are interconnected, how the system frequency will go. So that also you can see. So you can incorporate the all the renewable energy sources. So such kind of microgrids, if they are interconnected, so how to control the frequency with help of this renewable energy combination. Okay, now that also we can study in the in your future scope. And moreover, you can see that now if the more renewable energy sources as well as more electric vehicles. So one of the disadvantage or the one of the challenging task when you incorporate the electric vehicles, so those can be treated as load as well as the source. Suppose say if the particular area is having a more number of the electric vehicles, so if they are connected to grid to take the supply, so that condition is called as the loading condition. They will be acting as load. So if they are put for the discharge condition to the load, then they will be treated as source. Okay. So we don't know the exact patterns of the EV charging and discharging mechanisms as of now. So that is also one of the challenging tasks that we are having. You can perform that. And also you can see the impact of various renewable energy sources integration into the microgrid, multi-microgrid system. The same system like the conventional power system, you can study the impact of the intermittencies on the frequency as well as tail-end controlling problems in the event of especially the incorporation of RES are there, renewable energy sources are there. And also you can see the effect of the fax devices, how the fax devices are there, and the loads, various loads, frequency dependent and frequency independent loads and their sensitivity analysis. That also is possible. And one of the tasks that you can also do is, suppose if somebody manipulates the power system output, or the suppose say this controller where it is placed is some control center. So the inputs to this particular controller or the turbine are changed by some kind of attacker. So how you will mitigate that particular cyber attacks in view of the false data injections. So that also you can do. So okay, these are all are quite possible that we can compare and study for the further scope. And not only that, you can use the various newly proposed optimization techniques that are progressing and proposed recently, which are showing the prominent results with the existing optimization techniques. And also, as I said earlier, you can go for the incorporation of the efficient secondary controllers. As the system is becoming more complex with the incorporation of different renewable energy sources, which are intermittent in nature, as well as the different various loads, frequency dependent loads, as well as the energy storage system incorporation, and the electric vehicles integration into the existing grid, especially at the distribution level, the power system operation, that is control of frequency as well as voltage, may or definitely will become challenging task. And how you can cope up that particular challenge with the this particular optimization techniques and secondary control mechanism is of need of the hour, and you can also think in that direction. Okay, so as a whole, what we have saw in this particular presentation is the importance of the secondary controller and the comparison of different controllers, IPI, PID controllers for the interconnected thermal system as well as interconnected hydrothermal system. And we have proved that PID control is providing better responses. So these are some references. We can have plenty of reference from your IEEE as well as Science Direct websites. Okay, this is my presentation. If you are having any doubts or any kind of discussion, please, you can have that. Hopefully, you understood something out of this presentation. Okay, dear participants, if you are having any kind of doubts, please, you can message or you can ask me. Madam, are you there?
Yes,
Yeah,
sir.
yeah,
This is
yes, sir,
Dr.
we are
Jay Hari.
there, sir.
Okay, sir. Thank you. Yes,
Yeah,
please.
hello, sir.
Yes, sir. Please.
Yes, sir. Good evening, sir.
Yes, good evening, sir. Please.
Yeah, sir. So in most of the researchers, sir, they are using PI controllers.
Yes.
But in this system, PID controller gives best performance, sir.
Yes.
So
To see that,
how
especially if you go for the power electronics point of view, so in
sir.
that PI controller mainly used, because for the steady state error minimization, we will go for PI controller. But as the power system is very complex in nature, as the power system problem is very complex in nature, and we provide these controllers at the control stations. So more efficient controllers are required. So practically we are now using I controller only. So if you see that practical scenario, some papers are there, POSOCO papers will be there, power system operation control, that papers are there. If you see that they are using and suggesting for go for I controller. These are what your advanced controllers, PID controllers, fractional order controllers. They are also used in the industry and they will be applicable to this particular power system problem also.
Okay, sir. Thank you, sir.
Okay. So any other participant?
Please, I'm requesting participants, please, if you have any doubt, just you ask them.
So first of all, see that so first I should thank all participants for their patience to listen up to this time, evening time. So please, if you're having any doubts, I will share my
sir.
email ID also. You can email me, or you can ask your doubts in the chat also. In message box also, you can ask your doubts or any suggestion is required, can tell.
Sir,
Yes, sir, please.
sir, suppose in vehicle to grid charging application, sir,
Yes, sir, please continue.
to minimize the steady state error. So this PSY is useful, or sir?
Yes, yes. Actually, that depends upon the system that you are considering. So there is some kind of theorem is there. No freelance theorem. No
Sir?
freelance theorem says that a single optimization technique cannot be applied or cannot be applicable to all optimization problems. Means PSO may or may not be applicable to that particular system. We cannot say. So you have to apply that particular algorithm to the given system. So you are having the modeling of electric vehicles, EV fleets. So you take the group of electric vehicles and then apply in the area, in one of the areas, and you can see as they are working for, you can first see the application of these algorithm with various controllers, like for what we can say in charging mode as well as in discharging mode. Whether the suitable controller or the considered controller is able to provide the better responses. That you have to check, because there may be several permutations and combinations, because I controller may not work or may not work with PSO, PI controller, PID, fractional order controllers, 2 degree of freedom controllers, cascade controllers. That we have to check, and which controller and which optimization technique combination will work for the complex system that you are talking about.
Yes, sir.
Hopefully you have some.
Sir. Yes, sir. Yes, sir. Thank you, sir.
Thank you, sir. Next, any other doubt or any discussion?
Yeah, I think no more questions, sir.
Yes, sir.
Yeah. Sir, very thank you, and Dr. M. Raju, sir, you are explaining very nice with the different types of controlling systems. What is PID, what is PD, PI controllers, where they are used industrially or in academic colleges. You explained very nice. I hope if anybody having any doubt, just you ask. Otherwise, I will conclude that. Okay, sir. Sir, thank you very much, sir, for giving
Sir.
a very good explanation to us.
Sir,
madam.
before ending the session, sir, please all of you turn on your
Yeah.
videos along with our speakers, sir, so that we can take a screenshot. And Raju, sir, thank you so much, sir, for accepting
ma'am.
the invitation in a short time. Thank you, sir. Thank you so much. Dear participants, if you have any doubts, you can message us in the group also, WhatsApp group also, you can message us. We'll share resource person mail IDs so that if you have any doubts, you can ask through mails also. Thank you, Raju sir, once again. Thank you so much.
Okay, madam. Thank you very much, madam,
Thank
for
you, sir.
inviting me this particular FTP. Thank you. Thank you all
sir.
participants and
Madam, attendance link and feedback link, second session.
It's already
Yeah,
shared in the
I
chat
kept
box, sir.
Yeah, I kept in
Because of
chat
the
box.
net connection,
Not
it is
shared, sir.
not
Not
sharing, madam.
shared.
Can I share now?
In chat box,
Yeah.
not shared.
Sometimes
Wait,
it is
sir.
disconnected. It will not be open in a chat.
It
Not
is
disconnected.
visible to
Praveen
me.
sir, you can share
in
now
chat bo-
in the chat box
Yeah,
again.
again it is.
Already
Madam,
shared long back, sir. So again we'll share. No
yeah.
problem.
Session 2 not shared,
Okay,
madam.
okay, madam.
Not at all
Sir?
shared.
Not at all
long
shared.
back. Now share
Sound
it,
like it?
please.
Only
Session 2 not at all shared. Actually, share now.
First
Okay,
one,
okay,
Only first session is shared.
Oh.
Second session not shared.
okay, okay. I'll share it. No problem.
Maybe Praveen sir, please check
Ah,
while you are sharing. I think it is only
Yes.
one person access is there. So give it to all.
Okay, madam. Okay. Then actually it is visible to me in chat box. Okay, I will share again.
You share again. No problem.
Okay, no problem, madam. Once you check, sir, I shared that on attendance.
no. It is not in this chat box, sir. It is not reflected.
Not came, sir.
Sound like
Feedback
it?
link not came, not shared.
It is not it is not in chat box actually.
Chat box,
I'm
what
also
are
not able to.
section only, sir, not for second section.
One
Session
minute, sir.
section.
It is Samyukta, madam.
Sir,
Madam, it is
Sir.
visible to me in chat box what I sent, but
Okay.
why they're not
one
getting
second, sir. I'll share.
Yeah, yes, sir, madam. Because it is visible to me
I'll
what I
share.
shared
We'll
previously.
share.
Yeah.
Participants, please let me know. Is it now visible in chat box?
So
I shared.
Yeah, visible.
I shared.
Yes, now it is visible.
Is shared.
Okay, I'll share a
Attendance link
feedback
and-
link also. Just give me a second.
yes, madam.
Yes, I have shared both the links.
Yes.
Please fill the Google Forms.
Yes, shall we leave, madam?
Sir, we'll give 2 to 3 minutes, sir. So participants will give attendance and feedback. Those who have already filled the forms, they can leave the Zoom meeting. So we'll wait for 2 to 3 minutes, sir. After that, we can end.
Okay.
They are
Okay,
filling the form, no? So if anyone is missing, they will take. Okay.
Yeah.
I hope everyone filled the form.
Ma'am, can you wait some time? Just now I got the link in the chat box.
Okay, okay.
Yeah, it's okay from my side, ma'am. Yeah, thank you.
नहीं बहुत महंगा पड़ रहा है ये थोड़ा
Dear participants,
Thank you
done.
all.
Yeah, ma'am, please.
If it is done, we will close the session. I hope everyone give an attendance and feedback.
Yes, madam.
Yes, sir. Tari sir, please close the session.
Okay, madam.